honest. Yeah, this is so damn loud, this computer. But so let's see. To be honest, I've been now out for about a week or so. You know, sickness involved, not COVID. Doesn't matter, whatever. It's just difficult to take care of everyone and keep grinding with all this. But I've kind of come to a realization, which is that we're in February basically, and I haven't just I barely have done one exercise from the list here. So I'm almost like going to just rethink the whole thing, and I don't know whether I would just not spend the whole year with one very single super focused goal of just going through all the exercises. I think that's what I'll do. So I think I'll try to be a bit more realistic and say, well, I'm not gonna be like, I might work on the whole entanglement simulator on the side a bit, maybe do a couple of videos now and then, but I'll definitely leave that aside. And I'll definitely just not approach, you know, QFT and superdeterminism as of yet. But I'm rather, I think, gonna focus on the exercises, because like that's like a 300 pages book, right? And I've barely moved from you know, I've just done one exercise from the wave functions, and I'd like to go even more in detail, like to not just shy away from the math, because that is important, not to do so. And yeah, so this is it. So I want to take a look at, I wanted to do a quick session today, just a very quick one, probably half an hour or so, and try to maybe do a bit of a bird's eye view on these, and kind of try to have a bit of a realistic understanding of, like, is it going to be doable or not? But I think it should be. Why not, right? I've spent a fairly big amount of time focused just on problem one, but I think it's good because it helps me. And I'll come back to these in a second, because I wanted to. I've had some more thoughts about these today. But I was thinking one of the things that I could do is I could maybe change the approach a little bit, and actually go and say, look, we do one exercise, the first exercise of each chapter first, right? So we go like breath first, and then we go deep in each of the topics. And I could just go, I think I'm just gonna go and read the exercise. So wave functions is about wave functions. So that's page 1. And so there's about, like, you know, wave functions and whatnot. And then you're calculating things like probabilities of finding things in places and whatnot. And it's all like, that's actually helpful. I think I have a hint on why this is like that. And it's got to do with the fact that, this is awfully similar to the dot product formula with cosine or something like that. I think I saw this in a video that I was cosine formula for dot product. Look at this. Yeah, exactly. Because if I remember well from the other product, I have two terms like that, right? So that kind of makes sense. I have two terms like that, and I could just replace them with these, and then maybe there's some stuff happening there that makes the other term disappear and whatnot. But that would explain these. Yeah, but you can come back to the other video for that later, I guess. And so that will be definitely, that's a rote unblocking thing. But then we have problem 1.2. So we talk about normalization, we're talking about orthogonality, we're talking about expectation values. That is definitely helpful. What else do we have? Problem number 3. We have Hamiltonian in real values, real valued Hamiltonian, and so the question is what, like, okay, show stuff about the eigenvalues and whatnot, the periodicity of the system. 1.4 is look at these superposition of plane waves. What the hell? It's like there's an integral. Okay, so this is going to be interesting. Proof that these wave functions are normalized and orthogonal for free particle computer. So it's about, I think it pretty much is like these, right? So expectation values, it's about orthogonalities, it's about like, you know, we have a wave function, stakers have a real wave function up to a multiplicative constant. Okay, show about, you know, reason about momentums. Okay, so we're doing a bit of, you know, position and momentum analysis and stuff like that. 1.6 propagator. Okay, so that's cool because I think this is then path integral, right? Quantum mechanics, propagator. I think that's path integral, which would actually be pretty cool. We'll get into that. Awesome. Propagator. What the heck is that? Path integrals. Yeah. Yeah. Problem 7. Calculating propagators. Proving things like that. There's some heavy math involved in here, but that's good. Oh God. Normalized. Yeah, I use a complete orthonormal simultaneous arbitrary function gradually expanded. Alternative expansion. It's a lot of manipulation. Like I feel like it's a lot of manipulation, but let's see. Okay, so now we go to the free particles. So what do we do in free particles? Computer normalization factors, probability density. I mean, it's kind of a bit of the same, but just working with a free particle model, isn't it? Problem 2.2. Spherical waves. Satisfy the Schrödinger equation for a free particle of mass m, except at the origin. Give a physical interpretation of this non-conservation of probability. Okay, so some Schrödinger equation things. Okay, so this is just, it just goes a bit more in depth with, you know, with the actual free particle model, which is good because I think it's gonna help me strengthen that that perspective. God, baby, this looks dense. This looks dense. Position probability density, evolve wave function. Cool. So it's basically the same that wave, but it's focused on the free particle. What is simple potentials? Show that the angle of reflection equals the angle of incidence. Snell's law. What is Snell's law? Snell's law. Oh, that's Snell's law, the thing here. Okay, cool. I didn't know that's how it's called. Okay, so here's a bit. So this problem is more like the whole thing interacting. What is it? Simple potentials. Okay, maybe, I mean, that might be interesting because it seems there's something to do here with the environment interactions. For example, problem 3. Consider a particle incident on infinite planars. It's all about like it crashes with something where there's a potential, some potential energy or something. And then infinite square well. Okay, and then it probably culminates with the infinite well, a square well model. Cool, but it's going to be good to put some of the stuff in practice. So this is wave, this is still more wave stuff. This is about, like, you know, what happens when there's potential changes and whatever. The harmonic oscillator, I guess that is going to be standard stuff about the harmonic oscillator. I just want to spend enough time on all of these problems. So that's why I definitely think that I'm going to change the whole roadmap, and I'm just going to focus the entire year and getting the exercises done and getting acquainted with the math, and, you know, losing fear. Like, what the hell is this? Oh my god, like, I don't know whether I'm going to be able to digest things like this, and that's the solution, right? Angular momentum, what is this about? Consider an electron bound in a hydrogen atom under the influence of a homogeneous magnetic field. Ignore the electron spin. The Hamiltonian of the system is boom. The eigenstates boom, and then the assume for each of the following states, calculate the probability of finding the system at some later time. It's the angular momentum eigenstate. Is it then angular momentum another observable, or? Yeah. Yeah. Okay. So this is yeah, so this is cool. Next we will do quantum behavior. So a quantum system has only two energy eigenstates. Anytime, quantum behavior. Party measurements. Is this when we're getting into the discrete stuff or not? A pair of particles moving in one dimension is in a state characterized by the wave function like these. Discuss the behavior of and the limit. What would the solution look like? So the normalization constant and in the limit, this is sharply localized amplitude describing the situation where the two particles are at the distance. Keeping complicated. Einstein, Podolsky, Rosen. This is damn scary, man. This is super scary. Oh. Quantum behavior. Consider a neutron interferometer composed of 3 crystal slabs. A beam of neutrons is split in the first slab, reflected and redirected at the second, and finally superposed at the third and final slab. A phase shifter is placed along the route of one branch, giving a phase difference to the neutrons with which it interacts. A spin flipper that can flip the spin of a neutron is placed along the route of the other branch by placing the detector in one of the final beams. There's an interference pattern. The spin flipper device is based on the operation of a static magnetic field and a time-independent magnetic field perpendicular to it. What must be the relation between the neutron magnetic dipole moment and the rest of the parameters in order to have maximum spin flip probability? Ah, God, that's complicated. Okay, so this is, I see, this is a bit more generic, like you have like more of, you know, a set of kind of like specific setups, a bit of an experiment kind of thing, and then you have to reason about like what's the behavior going to be, and you know, okay. So that's definitely going to be interesting. General motion. A particle of mass m is bound in a spherical potential well. Find the energy eigenfunctions. Minimum value of the potential. General motion. A particle of mass m is bound in a central potential. The particle is an eigenstate, energy and momentum. Consider this operator. Expectation value. What does that category even mean? That section actually. A particle of mass mu is bound to a central potential. Is everything bound to central potentials? An isotropic harmonic oscillator is in an eigenstate of energy and angular momentum with energy eigenvalue. Boom. Viral theorem. Quantum mechanics. So that's the thing. The viral theorem relates the expectation kinetic energy of the quantum system to the potential. Okay, so that relates the kinetic energy and the potential energy. Cool. It's like realistically, how many hours can it take me for like a full problem, right? Because in a lot of these problems, I'll just have to actually research a lot of the stuff, right? Because that's the point. But I like that. I like just kind of jumping, you know, jumping to kind of like more the deep water, right? So, okay, many particle systems, maybe this is gonna be there's gonna be some entanglement stuff in here. Cool. So consider a pair of free identical particles. For simplicity, suppose they are moving in one dimension. Neglect the spin variables. Each particle is described in terms of real wave function, well localized. Show that if the two particles are fermions, then there is an effective repulsion between them. Compare with the case of two identical bosons. Solution: the given. Okay. Crazy, man. It's crazy, but at the same time, I gotta go through these. I want to go through these because it's gonna force me to learn even just like things like, okay, so what are then the fermions and the bosons things in here? Like, how does this relate to the problem? Is there any entanglement? Okay, no, there is actually. I thought there was no. That would be. Consider a system of and perform a measurement. Come to the fact that simultaneous measurements gives an outcome that can always be predicted from the first mentioned measurement. Show that this property entanglement is not shared by states that are tensor products. Okay, so these are the more fundamental. This is a more fundamental exercise, right, about entanglement and stuff like that. Cool. So there's going to be something. Well, that is what is this section? Section 6. What is the chapter 6? Why is this going so slow, man? Quantum behavior. Okay, so there's going to be some entanglement stuff in here. General motion and many particle systems. So yeah, that's going to be about many particles. And then approximation methods. Consider product of especially the first term, the column potential only in the region where a column is screened. The difference becomes negligible. Consider the difference as a perturbation and calculate the first order correction to the energy of the ground state. What the fuck is even that, man? Approximation methods. A particle of mass m moves in one dimension, subject to harmonic oscillator potential. The particle oscillation is perturbed by an additional weak anharmonic force. Find the corrected ground state and calculate the expectation value of the position operator in that state. Corrected ground state. Mechanics. Oh, why is it so? Ground state. Perturbation theory. In is a set of okay, so in quantum mechanics, perturbation theory is a set of approximation schemes accurately related to mathematical perturbation for describing complicated quantum systems in terms of a simpler one. Okay, cool. An additional perturbing Hamiltonian representing a weak disturbance to the system. If the disturbance is not too large, the various physical quantities associated with the perturbed system can be expressed as corrections to those of the simple system. These corrections, being small compared to the size of the quantities themselves, can be calculated using approximate methods such as asymptotic series. Okay. That's complicated stuff, man. But yeah, I think I hope I'm not gonna regret that. I hope I'm not gonna regret that decision. But and scattering. So what's scattering? Scattering. No, what is this? Is this the? Oh god, that's contour integrals, right? I have no idea what is that. How do you even do that? I saw these. Contour integration. Oh god. Along paths in the complex plane. So basically that's it. Yeah, I think that's what I will do. I think I just have to take it easy, and go one by one. And as I said, I think the strategy that I'm going to follow is going to be I'll go through every single first problem of every first session, and then I'll go as deep as I can, try to make sense of the solutions, making sure that my solutions match their solutions, and that actually we can make this work and gain understanding and get comfortable with the whole mathematical stuff as well. And I'll definitely already learned a lot by approaching the first exercise, which is almost, I mean, it's solved, but I just wanted to make sure that my intuition and my actual the formal part of it is correct as well, right? So where does this come from and whatnot and stuff like this, and then the whole thing with the current density is still a bit unclear, where is this formula taken from, and what, but now I understand and know what the current density is. Yeah, I'll leave it here for today. I still have a couple of the things that need to be taken care of, but we'll stick to it. We'll definitely stick to it, and I'm gonna try. So that's the roadmap for those who don't remember. But as I said, I think I'll push everything to 2023, and I'll literally just keep these as like 20, or these 2 points as like 2022. So I'm gonna, because I just, yeah, I'm gonna spend all the free time I can, all the time that I have for these streams that I can in this year, just focus on solving all the exercises in this book. And let's see what happens. Wish me luck. Bye.